Hello students and welcome to lesson 6.03 honors dealing with calorimetry. In the regular lesson we basically were focusing on calorimetry in the sense of taking a substance, usually a metal, placing it in the calorimeter, and of course there's a heat exchange between the metal and water, and then we can do some calculations to figure out the specific heat of the metal. In this assignment, we expand our understanding of calorimetry to include solutions, and then we're going to look at Hess's law. So we're basically just building on what you already learned in the regular assignment. So let's go ahead and get right into things. Again, we do have Common Core standards that we will be addressing in this lesson. You can pause the video at this point if you'd like and watch over, or read over, I should say, the ones listed here. You can also access these in the course by going to course information and selecting the standards. Again, for the 603 assignment, our main two objectives are to predict and calculate the energy transfer that occurred during a chemical reaction. And again, we are solving for a variety of calorimetry problems. To be successful in this particular lesson, you basically need to have an understanding of all of Module 6 up to this point. So in 601, thermal chemistry, 602, the exothermic and endothermic reactions, and then of course the regular assignment on calorimetry. Be able to solve problems using the Q equals MC delta T formula. So if you're still a little shaky on any of these, please go back and review the lessons. And you can certainly watch some of the recordings and come to the open tutoring if you need to get some extra help, but we do want to make sure that we're comfortable with all this material before we look at the honors assignment. Alright, so first we need to look at some terminology here. And the big term that we're going to be talking about is enthalpy change, or change in enthalpy. And sometimes you hear it called heat of reaction. Okay, all those different phrases mean the same thing. The symbol we use is right here, delta H. Remember, we've talked in the previous lessons that the delta sign simply means change in. And then we use the capital H here to represent enthalpy, because enthalpy again is a measure of heat gain or loss by a system during a physical or chemical change. So delta H is a symbol that we use. Now our delta H will always have units of kilojoules per mole. The reason being is, remember, when all the stoichiometry that we've done up to this point, everything is based on the mole, because we can relate that easily to the balanced equation. Alright, so that's why we want it per mole. And we use kilojoules because the joule, relatively speaking, is a small unit. So we like to use kilojoules just to make it a more manageable size of a unit. Alright, so very similar to when we were solving for Q back in the regular lesson. If we have a negative delta H, that simply tells us that the heat is moving out of the system, so it's an exothermic process. Just again, we want to emphasize that negative signs in this case do not mean we have negative energy. Alright, we can't have negative energy, but it just tells us the direction of the heat flow. If we have a positive delta H, then it's just the opposite. The system is going into the system, and that is an endothermic process. Okay, now we did mention just a moment ago that it is related to moles. So again, going back to what we've learned in stoichiometry throughout modules 4 and 5, the coefficients in that balanced equation give us the ratio between the reactants and products. Well, we can also use that to relate to the energy gained or lost by a system, because when we make the delta H per mole, now we have that relationship in place. Just like with molar mass, it's grams per mole, or molar volume is liters per mole. Well, now we're doing it with energy, kilojoules per mole. So in this particular reaction here, we have 1 mole of hydrogen reacting with a half mole of oxygen, yielding 1 mole of water, and that has a delta H, or change in enthalpy, of negative 285 kilojoules per mole. Alright, so that tells us then, if you look at the first interpretation here, 1 mole of hydrogen and 1/2 mole of oxygen react to produce 1 mole of, that should be water, sorry, and releases 285 kilojoules of energy. Alright, now let's say for an example we have 1 mole of oxygen. Right? We're given a problem, we're given this information, it says you have 1 mole of oxygen. Well, then that has to react with 2 moles of hydrogen, right? Because to get from a 1/2 mole of oxygen to 1 mole, we're going to have to double it, which means we also have to double the moles of hydrogen. So if I'm doubling my reactants, I'm doubling my products, which means I'm going to have to double my change in enthalpy. So if you look at this last bullet down here, it says if 1 mole of oxygen reacts with 2 moles of hydrogen, 570 kilojoules of energy would be given off. Okay, so let's again do another one here. Let's say the problem tells us that we have 4 moles of hydrogen. All right. Again, based on our balanced equation, we see that 1 mole of hydrogen gives off 285 kilojoules. So we can set it up like a conversion factor or a stoichiometry problem. And we can have 285 kilojoules per mole. Right? So the moles cancel out, so it's just 4 times 285. So in this case we'd have 1140, 1140 kilojoules of energy that is released. Okay, so just like we do mole ratio, we can also do ratio between mole and energy. All right. Now, to get all those numbers then, we have to use a calorimeter, just like we did in the regular assignment. Okay, but now we're going to look at solutions, because this is typically how we do reactions. We don't usually do just, metal and water. We typically have solutions. We mix them together. They either gain or lose heat, and then we want to calculate how much heat energy is gained or lost in that chemical process. So we're going to use a calorimeter just like we did in the regular assignment. If we're dealing with aqueous solutions, remember aqueous means it's in water. So there are some assumptions that we can do since it's a water-based reaction, if you will. First off, because it is an aqueous solution, we can use the total volume by combining both solutions. Second assumption is because we're using water as our solvent, then we can use the density of water to convert the grams, or excuse me, the milliliters to grams. And remember, the density of water is 1. So if we have, say 200 milliliters of water total, we have 200 grams of water. And again, since we're working with an aqueous system, we can also assume that the specific heat of water will be sufficient for what we're calculating. And again, the specific heat of water we learned in the regular lesson is 4.18 joules per degree Celsius gram. And then finally, don't forget that when we're all done, we got to make sure that the units are in kilojoules per mole. All right, so let's go ahead and look at an example of the type of problem that you would get. Let's say we have 50 milliliters of a 0.1 molar aqueous solution of silver nitrate. It's mixed with 50 milliliters of a 0.1 molar aqueous hydrochloric acid solution at 22.3 degrees Celsius in a calorimeter. The final temperature is 23.10 degrees Celsius. Calculate the enthalpy change. Okay, so first we're given the reaction right here. All right, let's check to make sure it's balanced. We always want to make sure we have a balanced equation. So we got 1 Ag here on the left, 1 on the right. So that's happy. Remember, polyatomic ions we want to treat as one unit. So NO3, we got one of those. And then on the right side we've got 1 NO3. So everybody's good there. We have 1 H on the left, 1 on the right, 1 Cl on the left, and 1 on the right. So this is a balanced equation. All right, the second thing is we got to pull out the information that we have, right? Now, always take what we're given and figure out what we have and where we're heading. Okay, so we're told we've got 50 milliliters of a 0.1 molar AgNO3, and that is reacting with 50 milliliters of a 0.1 molar HCl solution. Okay, and it starts at 22.3 degrees Celsius, and the temperature goes up to 23.10. Right, so that's the information that we're given, and we're being asked to solve for delta H. Okay? So let's take this step by step. Alright, first thing we need to do is go back to some of those assumptions that we talked about a couple of slides ago. First, we need to get our total volume. Now remember, to get the total volume, I can simply add the volume of all the solutions involved. So I had 50 milliliters of AgNO3, and I had 50 milliliters of HCl. So total volume, of course, going to be 100. Sorry, it's supposed to be a dot there. Milliliters of solution. Alright, remember, this is an aqueous solution, so it's in water. Now, because it's in water, we can then go to that second step, converting the volume to mass. Alright, and remember, we do that by using the density of water. And the density of water, again, is 1 gram per 1 milliliter. So of course it's a 1-to-1 ratio, so we have 100 grams. Now the reason we need grams is to solve for our Q. And remember, Q is MC delta T. Okay, what we learned in the regular lesson. So the M we just determined was 100 grams. C is the specific heat of water, so that's 4.18. Again, the units were joules per gram degrees Celsius. And delta T is the final temperature minus initial temperature. So our final temperature was 23.10, and our initial temperature was 20. 22.3 degrees Celsius. Alright, so plug this into our calculator. 100 times 4.18 times the difference between 23.1 and 22.3. Alright, and that's going to give us 334.4 joules. Okay, now remember, like we learned in the regular assignment, the heat that was gained by the surroundings was the heat lost by the system. So if the Q of the surroundings is 334.4, then the Q of the system is just the negative of that. And again, the negative simply means it is given off. So it's an exothermic process. All right. Now remember, it has to be per mole. Okay, so we need to change our HCl, or get the moles, I should say, of the HCl. Now you could do it for the AgNO3. It would be fine to use either one. In this case, they both were 0.1 molar. If they're different, it still would work. It's just a matter of, are you doing it based on the HCl or the AgNO3? And the reason being is, if you go back to the equation up here, remember it's a 1-to-1 ratio. So if you have 1 mole of AgNO3, it's going to react with 1 mole of HCl. So it really doesn't matter which one we use, because it's a 1-to-1 ratio between them. We just pick the HCl. Okay? So we were told that we have 50 milliliters of the HCl when we started. Alright, now we're going to have to first get that into liters. And the reason for that is, remember, our concentration, molarity, is moles per liter. Okay, so if we go back to our metric system, we remember there's 1,000 milliliters in a liter. So if we divide by 1,000, that gets us our liters. Then we can use the molarity. Back at the original problem, we were told we had a 0.1 molar solution. So that means 0.1 moles of HCl per 1 liter of solution. Alright, so by setting it up like that, you cancel out the milliliters, you cancel out the liters, and you're left with your moles. So the 50 divided by 1,000 times the 0.1, and we're going to end up with 0.0005 moles of the HCl. Alright. Now remember, we have to have kilojoules per mole. Okay, and this should be delta H here, not delta T. Okay, we got to get kilojoules. So going back up here to number 4, to get this to kilojoules, we got to do a quick conversion, just like we did with the milliliters to liters. Same setup. Alright, 1 kilojoule is going to equal 1,000 joules. So when we divide that, we're going to get negative 0.3344 kilojoules. Alright, so then in our final step, we're going to take that negative 0.3344 and we're going to divide it by our 0.005. Alright, and that would give us an answer of 66.9 significant figures kilojoules per mole. All right, now we need to look at Hess's law. Hess's law is basically a process where we write multiple steps and look at the enthalpy change over those steps, and then we kind of add them together to get an enthalpy change for a new reaction. Okay? In other words, if we look at the example here, carbon plus half a mole of oxygen gives us 1 mole of carbon monoxide. Then that carbon monoxide can react with half a mole of oxygen, producing carbon dioxide. Right? So that's a two-step process. Carbon going to carbon monoxide, and then carbon monoxide going to carbon dioxide. Well, we could also just go directly to carbon dioxide. Carbon, 1 mole of carbon, plus 1 mole of oxygen, giving us 1 mole of carbon dioxide. Well, if we take the enthalpy changes for each of the individual steps, we can add it together to get the enthalpy change of the one-step process. And that's all Hess's law is telling us. If you can take multiple steps of reactions and add them together to make a one-step process, then you can take the enthalpy changes and add those together also to get the enthalpy change of the one-step process. Now, there are some rules, I guess you could say, that you have to follow. All right, if for some reason you have to flip a reaction to, make things work out correctly, then you have to flip the sign. Okay, so that's one thing that we need to mention here. All right, if you flip a reaction, all right, and reverse it would be the proper term. Okay, if you flip the reaction, we use RXN as abbreviation for reaction, then you gotta flip the sign. Okay, change the sign. All right, and the other thing that sometimes will occur is the reaction as written may not have enough moles to balance things out, to cancel things out. So if you have to, say like the second one, if we had to double the CO, then we would then have to double the entire thing, which means we would also double the delta H, because remember that is based on the moles in the equation. All right, so if you have to multiply the reaction by a factor, then you also have to multiply the delta H. Okay? Whatever you do to the reaction, you have to do to the delta H also, because it is related to the number of moles. All right? And this will make some sense as we go through an example. But those are the two main things. Anything you do to that reaction, you have to do to the delta H. So if you flip it, you change the sign. If you multiply the delta H. All right, now like a lot of things in chemistry, the best way to do it is just to look at an example. So let's do this. All right, we are given the following equations. We have this top one here. And this one we got H3BO3 aqueous, that parentheses should be a little lower there, yielding HbO2 and water. And then we have the second one where H2B4O7 reacts with water. All right, and then we have the third one down here. And we need to find the overall delta H for the reaction here on the bottom. All right, so let's kind of look at the what we need at the end, and then we're going to have to work backwards. Okay? If we look over here, we've got H3BO3 on the left. Okay, if we go back to the original 3, we'll see that the first one has the H3BO3 on the left side, where we would want it. However, the balanced equation has 2 of them. So right away, there should be a bell going off telling us, well, I have to double that. So if I go back to my first equation up here, to get 2 H3BO3s, then I have to double this entire thing, including the delta H. So down here on the bottom, I'm going to rewrite that. We're going to have 2 H3BO3, and everything is aqueous, so I'm not going to rewrite that every time if that's all right. I'm just going to write their compounds here. Got 2HBO2, right? Again, we got to double everything. Plus 2H2O. And our delta H is going to be doubled. So that is now negative 0.04 kilojoules. Okay. Now again, we're going to look at what we need at the end here. All right, we have to have the B2O3 on the right side. So if we go back up to our initial reactions, we see we got the B2O3 on the right side for the second one. All right, but you notice there are 2 of them. Alright, so that's probably not going to work for us as 2, right? So we're probably going to need only half of that. So we're going to take the third one and we're going to take half of that. So we're actually going to multiply. In that case, it would be a 0.5 that we would be placing there, right? Sometimes we want to reduce instead of increase. So rewriting that one, we're going to have half of H2 B4O7. That's going to yield B2O3 and half of H2O. And then the delta H is going to be 17.5 divided by 2. That's 8.75. Now the second equation is going to help us as far as canceling out some stuff. Because right now we have HbO2. And you notice that we can't have any HbO2 on our products in our final answer. There's no HbO2 over here. So if we take the second reaction and we flip it, we can get this HbO2 on the reactant side. Okay? So the second one we're going to flip. Alright, so that's the first step we got to do here is flip the second one. Alright, so down here, our flipped second one, we're going to have 4 HbO2 and that's going to yield H2B4O7 plus H2O. And since we flipped the reaction, we need to flip the delta H, the sign of the delta H. So now it's going to be a positive 11.3 kilojoules. Okay, now we're almost there. Okay, now we've got things lined up correctly. Okay, but again, up here, we only have 2 HbO2s. In this reaction, we have 4. So again, like we did with that third reaction, we're actually going to have to do one more change to this third one. We're going to have to multiply that by half. We only want half of this thing. Okay? So when we multiply that by the 0.5, we now get 2 HbO2, and that's going to yield half of the H2B4O2 half of a water. And again, remember we're talking moles here when we're dealing with these halves. I mean, don't think it's a half molecule, it's a half mole. And then we're going to take half of 11.3. And that's going to give us 5.65 kilojoules. Okay, and then again, this reaction, right, that one is now not being used. Okay? Alright. So now after all of that, if we add these three reactions together, we can start canceling some stuff out. Okay, and what I mean by that, on the right side of the arrow here, we've got 2 HbO2. That cancels out with the 2 HbO2 on the left side of the arrow. Okay, so anything you see on the right side of those three arrows, and if it's on the left side also, we can cancel it out and get rid of it, because that means it was present before and after the reaction, so it's not involved. So we can also do the same with a half mole of the H2B4O2. Alright. Now, with what's left, if we combine all of those into a final reaction, we have 2 H3 BO3 on the left side of the arrow. On the right side of the arrow, we have B2O3, and we have all this water that we can add together. So we've got 2 waters here, plus a half here, so that's 2.5, plus another half, gives us 3 waters total. Alright, so when we compare that to the equation we needed, you can see we have the equation we need. So now we just take those 3 delta H's and add them together to get the delta H for the reaction we're looking for. So we've got negative 0.04 plus 8.75 plus 5.65, and that gives us a final answer of 14.3 0.36. And again, the units are kilojoules per mole. Okay. Now, something I do want to mention here, this particular problem was picked because it pretty much did everything. We had to do some doubling, we had to do some halving, if you will, some reducing. We also had to do some flips. Okay. Generally speaking, the type of problem you'll see will only have maybe one doubling and one flip. It's not going to have this many steps to it. But you can see the principles in practice in this one problem. Okay, where we had to do some flipping, we had to do some multiplying. All right, but that's Hess's law. By taking those three equations and manipulating them, we were able to get the one that we needed, and then we can just simply add the delta H's together to get the delta H for the new reaction. All right, so that again is the lesson. Make sure you go into the lesson and finish the examples and practice problems there. Click on any hyperlinks you may find. If you need some extra help, please attend the open tutoring sessions as needed. There is a review sheet in the Resource Center you can use. For your assignment, you're going to have the 603 Honors Virtual Lab. And if you are doing that lab and need some help, we do offer completion sessions. So you can check your teacher's announcement page for the schedule to see when the next completion session comes up, and you can join us and we'll walk through that with you. Please be sure that you watch the pre-video before you attend and have completed the requirements explained in that video. And of course, once you have your lab report done, you can then submit it in the assessments section in the course. So I hope this was a helpful experience for you, and we look forward to seeing you again soon.